Net talk. The speaker for today's talk is Professor Muhammad Firdaus Raih, Chair of Department of Applied Physics, Faculty of Science and Technology, University of Kebangsaan, Malaysia. He has a bachelor's in molecular and cellular biology and biochemistry from University of Kebangsaan, Malaysia, and a PhD in molecular biophysics from the University of Sheffield. Firdaus' research is in the field of bioinformatics and molecular biophysics. His research group focuses on the computation analysis of macromolecular structures and the discovery and characterization of genome-encoded non-protein coding elements and regulatory systems. Professor Muhammad Firdaus Raih, please.
Thank you, Professor Gromiha. I'll begin my screen sharing.
Yeah.
Okay, I hope everyone can see this. All right, good morning, everyone. And I think maybe for some of you in the east of my position would probably be good afternoon already. First of all, I would like to thank APBioNet for giving me this opportunity to share a bit about the research that we have been doing in our group. And as introduced, my name is Firdaus. I'm with the Department of Applied Physics at Universiti Kebangsaan, Malaysia. I'll be talking today about 3D substructures and a bit of an overview of what I'll be talking about. I'll be covering what is a 3D substructure, why do we want to study them, how can we find and compare these substructures, what can we use the results of the searches for, and how can we translate the result of our researches to more widespread use. So I think many of us are aware that the vast majority of the data in biology is generated from the sequencing of DNA. And what you get, the output of DNA sequencing, are basically just this string of letters that represent the DNA. In this case, this is my gene, which that DNA you can then translate into a protein sequence. And the abundance of these sequences means that there are many of them available for comparisons. And the most common analysis in bioinformatics is using these sequences in the form of alignments. So we are using these alignments like this to gain insights into the function and evolution of biological macromolecules. This is fine because there are rules that allow for such extrapolations and information transfers to take place. But we must consider that proteins do not look like these at all. Instead, proteins can fold into a three-dimensional shape, and that three-dimensional shape allows them to carry out their functions. So in a way, proteins look like this. So the sequences do not provide the structural context or the direct insights that into function that the structure will allow. And we also know that the structures are also more conserved in evolutionary time, long after the sequences have diverged. So these structured data are archived or placed and accessible in a database called the Protein Data Bank. So this is basically a repository of the structure coordinate data for biological macromolecules. And as I mentioned, they are coordinate data. So basically, they are stored in the form of Cartesian coordinates. So in this case, you get X, Y, and Z for the third dimension. And this is the legacy PDB format. And now it's moved on to the CIF format. But you can still see that here, there's information about where the atoms are in 3D space. And here you've got the amino group for valine, C alpha, and so on. And currently there are in excess of 175,000 structures in the PDB. This is very much lower compared to what is available in the gene bank database for sequence data. Looking into the context of the current pandemic, there are now 24 SARS-CoV-2 protein structures available in the PDB. And in total, there are actually 1,018 SARS-CoV-2 structures. What I mean by that, here meaning that there are 24 proteins, but those 24 proteins are represented by maybe 1,000 over structures. This is because some of these proteins are the exact same thing, but maybe have different ligands. So why do we study these structures? Because the structures show the macromolecule as it really is and not as a representation. And we also know that these structures are more evolutionarily conserved than the sequence. Therefore, we can see similarities in the structure that are associated to the function of these structures long after the sequences have diverged or evolved to become something else. So I repeat again the title of my talk, and what I want to talk about now is the 3D substructure. And I want to define this 3D substructure here as constellations of residues that are the components of a complete or larger macromolecule. So we're talking about constellations of amino acids that are components of proteins. These are quite often in literature termed as 3D motifs or structural motifs, but I avoid that term structural motif here because in some of the cases, it is not a repetition, therefore it is not a motif. So why do we want to search for these substructures and why do we want to study them? Let's take, for example, this aspartic acid, histidine, and serine grouping, which makes the serine a very strong nucleophile. And this arrangement of amino acids is found in several totally unrelated proteins, such as trypsin, satylysin, and even lipases. And these are actually the what is known as the serine protease catalytic triad. And these are active site residues that are identical and used for an identical function. Again, I show that arrangement in two completely different structures. So you can see here that the arrangement is identical or similar, but the rest of the structure is not the same at all. If you can follow the folding, it's quite different. And one easy way to focus on that is just by looking in this corner here, so clearly that it is very different from each other. So these similar arrangements of amino acids leads to similar chemical activity, even when there is no full similarity. Again, I show that here. You can see that when the two proteins are superposed, they're actually quite different. But the active site residues actually come together quite well. So different enzymes can carry out catalysis using the same reaction mechanism, even though they are not related. So in such cases, in cases like this, it's possible that it is an example of convergent evolution. So now I want to move on to the methods of how we find these 3D substructures. One common method that we use is a graph theory. Now, graph theory is basically a branch of discrete mathematics, and it's something that almost everyone here will probably have used before. We probably know it as Google, Waze, Facebook, and many other apps. But in bioinformatics, the use of graphs or graph theory is quite widespread and quite common. We use them in sequence database searches, the alignments, genome assembly, and even studying pathways. But for this discussion, I will focus on the use of these graphs for finding substructural similarities. Now, in graph theory, a graph consists or is said to consist of nodes, sometimes called vertices, and edges. And it is these edges that describe the relationships between the nodes. The edges can also be vectors, meaning that they can have direction. Now let's go back to the example of that serine protease catalytic triad. So here we see the three residues, and let's put dots here. And by putting these dots here, we can see that perhaps these amino acid side chains can be the nodes of a graph. And perhaps the distance between them can be the edges of a graph. Now let's take that a step further or a step higher. We will try to represent the 3D side chain arrangements as what we call pseudoatom vector graphs. Now they're pseudoatoms because you take a whole amino acid side chain here. Instead of representing all the atoms, we only select representatives, and therefore these are pseudoatoms for that particular residue. And we call them pseudoatom vectors because they have direction. Okay, so this will have a direction. And we can then use this to represent the amino acid side chains instead of an all atom representation. So again, let's look at that serine protease catalytic triad. And now we represent them as the pseudoatom vectors. So here represents the histidine, and this represents the aspartic acid, and this will represent the serine. Now, as I mentioned, the pseudoatom vectors will have direction. So we've got a start point and an end point. Okay, and we can then try to calculate this distance between them, so then we can get the edges of a graph. So let's take this the vector for aspartic acid to histidine. Okay, so this is the end point of the vector, and we measure the distance to the starting point of this vector. And the distance there is 3.6 angstroms. And then we try to map these values into a table that we can use later as a matrix. So where is this? Where can we put this on the table? So histidine here to aspartic acid here. We've got the start point and the end point. So that's start to end of histidine, of the histidine to aspartic acid. Sorry, the aspartic acid to histidine. Now we look at, it can also fit here where you've got the aspartic acid to the histidine. So ES, and we can then put the values in there. And if we were to do it for all the distances that we have defined here, we would then be able to fill up this matrix. And then this matrix we can compute to find other similar matrices using a subgraph, by solving a subgraph isomorphism problem. So the substructure, which we represent as a matrix, we can then search for them in a larger structure, maybe a protein structure, using subgraph isomorphism algorithms. And we are able to find similarities of this inside a larger structure. Okay, so we can use this substructure as an input to find occurrences of the same or similar arrangements in other protein structures. And we can then take the rest of the structure and other protein structures, also represent them as graphs using the same scheme and carry out the searches. So let's assume that this is a cartoon representation of a database. So let's assume this is a database of protein structures. So we had just now a query. So we want to find that serine protease catalytic triad in this structure database. So, and here it is. Okay, so using that subgraph isomorphism problem, we are able to find that occurrence in a structure database. Okay, so this is, of course, a simplification of the process, but you might then question, wouldn't such a search be too rigid? And it will be very difficult to find substructures that are not exactly arranged as per the query. Just now, remember, we define the values of the distances very specifically. So in reality, those values are not going to be always the same. So what we do to that, the answer is yes, it is very rigid. So we introduce flexibility by employing a distance tolerance parameter. Okay, so let's say 3.6 angstroms just now for that distance between the ES of the aspartic acid and the histidine. By employing a distance tolerance parameter, you've got a sort of a sliding window. So instead of just 3.6, you can say a distance tolerance of 1.5 angstrom. So it can move up and down 1.5 angstroms. And then we can once we have found the correct similar matrices, we can then compare how they overlap using least squares superpositions. Okay, right. So then you might also question, it sounds very obvious, it's a very obvious problem and a very obvious solution. But the answer to that, again, is yes, it is very obvious, and it is being done in many structural searches. But for most of the other methods, they will use the C alpha backbone, while our method focuses on the use of the sidechain representations. And this does offer advantages to the search, which I will demonstrate in this slide. Here, what you can see is that uh, the side chains here superpose quite well. Okay, so as we know, the business end of the amino acid is going to be the side chains. These are the ones with the features. These are the ones that are going to be interacting with other proteins, other amino acids, other ligands. And so we want them to superpose if we want to infer the same function. But in this case here, it is clear that although the side chains superpose, the C alphas themselves do not superpose. So if you were to do a C alpha superposition, you would not be able to find this example here. So now that we've developed the methods, what can we do with this method? So we want to go into the applications of this search. So we were thinking, perhaps we can find similar substructures in unrelated or very highly divergent proteins. And this can help assign functions to proteins that may have unknown functions. And to make it easy for other people to use, we have developed those algorithms and deployed them as web servers so that other people can use them. So there are two of them that have been deployed. One is called Sprite, and the other one is called Asem. The difference here is that for Sprite, the input is a whole PDB structure, and it searches a motif database. Whereas for Asem, the query or the input is a motif, and it searches PDB structures. Okay. And this is one example of how the searchers have been able to provide insights into shared function. This is a paper impressed by Israel Silman at the Weizmann Institute. And they're perhaps one of our hardcore users of the ASEM program. And this analysis was done by Joel Sussman, who is a founder of the Proteopedia page. So if you haven't heard of it, I suggest you Google Proteopedia. It's a very good sort of Wikipedia for proteins and protein function and protein structures. Anyway, back to the topic at hand. So what they have done is they were looking at acetylcholinesterase in a stingray, Torpedos californicus, or something like that, if I'm not mistaken. And they found this uh, arrangement consisting of four aspartic acids. Okay? And because that arrangement seemed interesting, they did an ASAM search to find other examples uh, of occurrences where you can find four aspartic acids quite close together. And they were able to find these four different examples in different organisms doing slightly different things. In general, they are all metal binding sites, but in this case, you've got it's binding, it's a phosphodiesterase binding to two calcium ions. Here is a pyrophosphatase binding to three magnesium ions. Here it is a diphosphate synthase binding to a magnesium ion. And here it is another phosphodiesterase, but binding to two manganese ions. So clearly that what they have called this 4-aspartate or 4D motif, and it's a very interesting metal binding motif, which they are reporting in protein science and is currently in press. So we know that we can find the 3D structures in unrelated or highly divergent proteins, but can we also use that for applications like drug repositioning? So using ASAM, what if we know what a drug binding site is? So we can take known drug binding sites, and perhaps we can find examples of those known drug binding sites in other protein structures. And yes, we were able to do that. And the findings of that we developed into a web server and database called a drug reposer. Okay. So if we can find, we can reposition approved drug compounds to treat other indications and diseases, can we use this in a real world application like cancer, antimicrobial resistance, or what's currently affecting us greatly, COVID-19. So we decided perhaps we can do a case study on COVID-19. And we were able to publish that paper last year by looking through the available SARS-CoV-2 structures and seeing if we could reposition existing drugs into these structures as a possible means of drug of therapy for them. Okay, and one interesting finding for that we found that the SARS-CoV-2 ADP ribose phosphatase has actually multiple sites that could bind to different compounds. Okay. Now, if we could find similar binding sites in other structures for the drug compounds, this also means that that drug could bind to unintended target. So could this unintended binding cause toxicity or other side effects? So uh, in essence, we could use the same method to explore whether a drug that has been repositioned could result in any potential side effects to an off-target site. And we were able to find some examples of that. However, do take note that knowing off-target sites is not a bad thing. Why? Because by knowing these off-target sites, it means that the clinicians and the trial programs can be provided with the necessary intelligence to avoid surprises, and it will allow them to mitigate the side effects and assess the cost benefits of the off-target effects. Okay. Now moving on, since we could find an alternative target to a compound, could we also find alternative compounds once we have found an alternative binding site? So in other words, if we know the alternative sites, can we then stick something else in there instead of the compound that we started with? And yes, we could. We found that we could find examples of that happening, and this could perhaps increase the efficacy, or in some cases, increase the tolerance amongst different individuals. And it can help a lot towards precision medicine, where you can give or prescribe different drugs to different people based on their suitability. Okay. So yeah, we could use it for drug repositioning, but could we also perhaps just explore the structures available in the PDB and see what we could find using these graph theoretical programs? Of course, as Sam just now, it's not suitable for exploring because you need to do a specific search. So you must know what it is that you're trying to search for. What if you do not know what you're trying to search for? So we came up with, by using that same algorithm, we came up with something, a program called Imagine. Okay. So in this case, instead of giving a specific search, we can provide a more generic search in the sense that if you have a rough idea of the chemistry that you would like, you can then submit that and do a search to find other similar chemistries. Okay, and we were able to carry out such searches, and in doing so, we could find conserved motifs in unrelated proteins, uh, and that we could that perhaps investigate and identify novel motifs from there. An example here is this zinc binding function of this tetrad consisting of histidine, cysteine, histidine, cysteine. It's possible here that the proximity of this could also have a disulfide bridge. So we could have a redox mechanism for metal binding here as well. Okay, and clearly here, these two proteins are unrelated. Okay, so when you superpose them, you could see that they come together very well, but the two proteins themselves are very unrelated. One is one is the dimerization domain of a recombination activating protein, this one here, and the other one is a zinc finger bound to DNA, as you can see the DNA here. And if we were to look at these residues, in this case here, it almost seems like there is an alignment there, but that is not the true alignment, because where it aligns to is actually here. Okay, so if we were to look at the pairwise alignment, there is no similarity that we can extract at all from that alignment. Okay, but yet we can extract and find that similarity in the 3D superposition. These are other examples where we were able to find novel motifs that are detectable only in a three-dimensional context. What this means is that you have a motif which consists only of a single residue at sequence level. Now, normally, a single residue is not considered a motif, but given the context of the structure, we are actually able to see that it is a motif. And perhaps one question is that, can we transfer this knowledge to sequence level searches using machine learning? Okay. Using that same Imagine program, we decided to search for repeats and symmetrical arrangements of amino acids. And from there, we were able to find quite a number of these motifs that are present at the intermolecular context interface of quaternary structures. So here, this is a trimer, okay, and in the asymmetric unit, you've got two histidines that contribute to this interface that you can see here. Okay, and we have made this into a database called ICBMs. Okay. Right, so that works for proteins very well, but what about other biological macromolecules? One interesting area that we could try is, can we use that same graph theoretical searching for RNA structures? There is increased interest in RNA structures. As you can see here in the PDB, you've got a drastic increase in depositions of RNA RNA chain containing structures. In the early days, there were not many of these. So using that same concept of pseudoatoms, we tried to do it for, instead of amino acid side chains, we tried to do it for bases. And yes, we found that we could carry out a similar search using a pseudoatom representation of this for RNA. And in doing so, we were able to find novel motifs that have not been reported in literature. And in this particular one, although it may not be obvious to you here, what you've got is a UAU and the exact same UAU stacked on top of each other. And this is actually at an intersection of 3 domains in the ribosomal, in the large subunit of the ribosome. So clearly, and this is very highly conserved, and we've managed to find it in almost all bacterial ribosomal structures. Since we were able to do drug repositioning in the protein structures, could we also do drug repositioning for drugs that target RNA molecules? And to do that, we use a case study of paromomycin. And in this case, we found that yes, there are actually similarly arranged sites in the ribosomal subunits that can be used to retarget this antibiotic paromomycin. So it is also applicable not only in proteins, but also in RNA structures. And again, to make it easy for people to use, we have converted the algorithms into web accessible interfaces. One is called NASAM, which is very similar in operation to the ASAM and Sprite program I mentioned just now. And another one called Cognac, which basically looks at clusters of hydrogen bonded bases. And we use these 2 programs to annotate RNA structures in the PDB, the results of which we present in what we call the internal database, or interactions in RNA structures database. Okay. So now I want to move on to the final part of the talk. So we've covered methods, applications. Now I want to touch on where do we go from here, the directions. So one that we are very much interested in and currently doing is trying a more systematic whole PDB scale deployment of the methods to annotate and characterize substructural similarities in known and unknown structures. And we want to take that further as well. For example, just now I showed you some residues or tertiary 3D motifs that are considered motifs in a 3-dimensional context, but they would not be considered motifs in a sequence or 1-dimensional context. So what we want to do is see whether we can use machine or deep learning approaches to learn from the environment surrounding those residues and see whether we could then apply a sequence level searches to identify those single residues as a motif. And again, using this methods, it would be quite interesting if we could model the evolutionary trajectories of the substructures. One example that I would like to show for that is this example here. Let me go back a bit here. So you can see here in a very conserved folds for these seven uh, subunits. And you can see that in some cases you've got arginine, but in other cases you've got lysines. So if we were able to model the evolutionary trajectory, or maybe a synthetic evolutionary trajectory, perhaps we will be able to come up with novel functions for some of those existing structures. And as I showed you just now, there are a whole lot of exciting possibilities for RNA structures as more and more of them become available. So again, we want to do what we have done for the proteins, for the RNA structures next. Okay. So in conclusion, the 3D substructures such as in proteins and nucleic acids, RNA, can be carried out by representing the amino acid side chains or bases as graphs. And these work very well, and they work quite fast. So a single SM search can take within, can be completed within a few minutes. Okay, and such structures can allow for 3D substructures to be found in a database of structures, or vice versa, in the sense that you find known motifs in an unknown or uncharacterized structure. And being able to find such substructures have allowed us to uncover gems that are hidden in what we call blindingly plain sight. It's right there in front of you, but because we cannot see the context, we are not able to understand that. Okay, and the annotations of this have also allowed us to explore alternative targets for the repositioning of approved drugs. And as we've got collaborators who are using drug reposer to actually identify drugs for certain types of cancer. Okay, and our discovery of the interface motifs can perhaps also contribute towards a deeper understanding of how proteins can assemble into functional quaternary structures. Okay, with that, I've come to the end of my talk, and I would like to acknowledge all the collaborators and the funding I have received over the years. Um, the late Peter Artemiuk, who worked with me on the developments of the programs, and with Peter Willett. uh, I've received funding from various sources, which includes the Ministry of Science, Education, UKM, the University of Malaya, BBSRC, and the computing resources that are hosting the services, the web services at the Malaysia Genome Institute and the Advanced Medical and Dental Institute in University Science Malaysia. And of course, it's impossible for me to have done any of that without all these what I call labor camp inmates, or politically correct terms, students and postdocs. And with that, I would also like to take this opportunity to invite all of you here to participate in the Asia Pacific Bioinformatics Conference, which is happening next year, the 20th edition of APBC, which is APBC 2022. This is happening early next year, 25th to 27th January. The submission deadline is sometime after the middle of the year, and I do hope to see many of you there. We will be holding this as a virtual conference, and we're not trying to make money, because this is we're doing this online. So The fees that we're going to charge is as little as possible, mainly just for the registration and administrative purposes. And I do hope to see many of you there. Thank you very much, and I hand the session back to the Secretariat.
Thank you, Professor Firdaus, for your excellent talk, and thanks for maintaining this time. So now this session is open for questions and discussions. And the participants, if you have any questions or comments, I think there are several questions in the chat box. First question from the graph theory, how do we determine the item in a substructure to be the vector when calculating the distance between vectors? Is it the central point of substructure?
I can try and answer that. Basically, for proteins, we use the amino acid side chains, and for bases we use the bases. And how we determine for the amino acids is we try to take into consideration the key bits or the key functional elements of the side chain. So if you know that something is going to be negative, the charge is going to be at a particular point, that's where you sort of make your vector. Okay, so this was sort of very manually fine-tuned for the 20 amino acid residues, and the same is also done for the bases. So it's got to be fine-tuned a bit. So although the searches and all that is very easy, is the fine-tuning of this curing system that took a lot of time and testing. So we wanted to make sure that if you put in a histidine, serine, asp arrangement, it is going to be able to find that and not something else. Okay, and that's where a lot of it has been fine-tuned. I hope that answers your question, Tandy. And Nisha, I think, asked, is there any statistical significance employed to show the differences? We use RMSD to show how similar they are. So that's why I said, once we have found a similar arrangement, we then superpose them using least square superpositions. So it's basically standard. If you're used to less carb, then it's basically that, LSQKAB. Is least square superpositions, very much Caps and Shander style, very old school, nothing complicated about it. And it's the RMSD values that we say how similar an arrangement is. Other than that, there is no statistical analysis involved, because basically it's a matching of the matrices. Okay, so it's not a prediction, it's just a matching of the matrices. We're not trying to predict anything, so we're not putting any statistics onto it. The interface comes with visualization, embedded visualization interface. So once you've found a match, you can basically click on it and see how well the match superposes onto your query. Okay. I hope I answered that, Nisha. Xiaoxian Ao is asking that can generate the matrices in, yes, as I mentioned, for our programs, we generate the matrices ourselves, but you can design your own matrix if you want, okay, and using the scheme I said just now. So how do you want to define your edges? If you understand the graph theory, you need to define what you want to use as the node and what you want to use as your edges. So edges, in our case, we have used the distances between them, but we have also used hydrogen bonds as edges as well. So if something is hydrogen bonded, that is an edge, and the hydrogen bond donor and acceptor are the nodes. So it depends on how you want to do it. You can actually define your own matrices by deciding on what you want to use as the node and the edge. Okay, I hope I've answered that question, Zian Ao. Another question is from Ziqing Tan. What are the prerequisites for discovering the substructures of proteins? I'm not quite sure I understand that. The prerequisite is basically you must know, if it's a discovery, then you must do the work to make sure that it is new. So you have to go through the literature, you must go through PDB records to make sure that it's not been reported or mentioned before. I'm not quite sure I understood that question, but that's my answer for it. Can we use this method to find a pharmacophore? I've never done it. So I'm not able to quite answer that question. But basically, we have to look at it from the binding site point of view. So if you know what you expect to be the binding site, you can perhaps find other similar binding sites. Okay. Khairul Baria is asking, what is my opinion on substructure searching versus MSA? Is substructure searching more effective than MSA? If MSA is multiple sequence alignment, then there is solving two different problems. They can complement each other. Like I said, the substructure searching can find examples of very unrelated functional residues that may not be aligned. And we can use the MSA to basically see how different the two proteins are, but you can probably already see how different they are from the structural alignments. It's not a matter of separating substructure searching and MSAs, but complementing. So if you've done a substructure search, perhaps you want to do an MSA to fill in gaps in your understanding of that. Okay, I think I've reached to the, at the bottom of the page. So,
yeah.
Please, there's one left there. Suggest us the research article for graph theoretical searching. I'm not able to suggest any specific ones because, like I said, in biology, we use graph theory for lots of things, including a lot of the sequence alignments, sequence assembly, pathway analysis. So it depends on what you want to do. You can probably find a review paper that's relevant to what you want to do.
Good. Okay. Yeah. Yeah, Professor, I have a couple of questions. Right. It's an interesting and informative talk because you used graph theory approach to identify the substructures in proteins, and you could delineate some of these important interactions as well as the clusters from the protein structures.
Yeah.
That is very interesting. And so I have one question. One is, for example, if you consider this number of residues involved in these substructures, for example, the clusters. So up to how many residues you can connect with these substructures?
Right.
Three residues. Yeah.
Thank you. That's a very good question. We can go up to usually 8 to 12 residues. So the maximum we can do is 12 residues. Why we selected that? Because as you go bigger, it doesn't make sense as a substructure. So, you know, you could get lots of random discoveries. So the smaller it is, the better. We can even search two residues, but two residues will also not sometimes make sense because you find too many things.
Yeah.
But 3 to 6 residues is usually what we use a lot of. Having said that, we can go as high as 12 residues, and we have found some interesting things at even 12 residues.
Yeah, because the way I'm asking this question is because if you go with a more number, the number of occurrences will be less.
That's
Right?
right.
The less number of residues, you'll get more number of occurrences. And
Yes.
my next question is, if you find this type of number of residues and occurrences, whether these clusters are from the proteins of similar functions or similar structures, or you could see the clusters completely diverse functions or completely diverse structures
Uh,
based on
uh,
fold or families, superfamilies.
so that's a very good question. As I showed just now, in one example, they can be totally unrelated at all, but it is just
Yeah.
the cluster that is the same function. But in some cases, we also see very highly divergent structures. So they are related, they are homologous structures, but when you do the sequence alignment, they're hardly detectable that is similar. But when you do the full similarity, you can see that it is similar, and the superpositions actually they superpose quite well. One example I did not show is we recently found a Cas2 protein homolog that you couldn't really see from sequence similarity because it's under 30% identity. So that's very interesting. But when we did the full similarity, it's very similar, and the active sites actually superpose quite well.
Yeah, good. Interesting. Yeah, my last question is, when you discussed about COVID-19, the proteins, you use the static structures available in the PDB to identify the similar substructures.
Yes.
Could you please comment on these structures if you do the dynamical structures? For example, if you do the MD simulations and generate a large number of structures, you can identify same substructures, or this will change because this depends upon your distance criteria 3.6
Yeah.
angstrom.
So yeah, you're quite right there. In our case, we have used a very the distances are fixed, but there is some a leeway because
Okay.
we, like I said, we have introduced a distance tolerance parameter so that it's not too rigid. So even if the pocket is not very similar, you might still have some similarity in terms of to the original compound binding site.
Okay.
So yes, it does take into account some dynamics, but we did not do any molecular dynamics study on it.
Yeah, yeah. Okay. Good. Thanks. Yeah, I think
Thank
that we have few more questions in the chat box.
Okay.
The time is 9:25 still. It's okay.
I'm not sure whether
The Calista is one question. If we got
uh, yeah, I think here we've got a molecular structure of a compound. Is there a way to find out how it will interact with different protein structures? I think this is a problem for docking, Callista. So it's not what I was talking about just now. It's more of a docking problem. So you can try and investigate if you've got the compound, you can try do docking with different target structures. Okay, I hope that helps. But it's basically not what we were discussing just now. Okay, I think
good.
I
Yeah, if I think no more questions,
yeah.
thank you, Professor Firdaus, for your descriptive and very informative talk.
Thank you. You're
Okay.
Thank
welcome.
you. Thank you very much, Prof. Firdaus, and also thank you very much to Prof. Michael for moderating the talk. So I think it's time to have a photo session. I would like to invite everyone to open their camera. I'll allow the camera sharing. Okay. Can you all turn on the camera for us to have some photo session together? Right. I'll wait for about uh, 5. Can you all start the video? I have enabled starting the video.
They're all very shy.
I think perhaps from ours, I can't start the video. There's someone.
Oh, okay.
Thank you for the. Okay. So can you all try to start the video again? Okay. I think it's okay now. Sorry. I think still can. Okay. Hang on for a few minutes. Start video. Okay. Sorry. Sorry. Okay. Now I think it's can. Okay. Now we see faces. Right, everyone. Hi, Mr. Paul. Hi, Prosetti. All right, I think we can start the first taking of photo now. Smile, 1, 2, 3. Right, another one. 1, 2, 3. Right. Okay. Thank you so much, everyone, and we hope to see you in our next APBioNETTalk. Please do subscribe to our YouTube channel, and thank you very much once again for our speaker and for Prof. Michael as our moderator.
Thank you.
Bye bye. See you, everyone.
Bye.
Have a good day.
Bye. Have a good day.
Thank
Bye.
you.
Yeah. Bye, Firdaus.